Okay, hello everyone, and welcome to Emory Climate Talks. My name is Eri Saikawa, and I'm an associate professor of environmental sciences at Emory University. This webinar series is made possible by our anonymous donor that supports our trip to the UN climate change negotiations. And Emory Climate Talks is in partnership with the Department of Environmental Sciences and the Resilience and Sustainability Collaboratory at Emory University. As usual, I would like to thank Leah Thomas for doing everything behind the scenes. Thank you so much, Leah. I am so very excited to have so many folks today, and I know that some of you are joining us for the first time. Welcome, and thank you to the regulars that came back to join us as well. As you might have noticed, this is being recorded, and we post most of our webinars on our YouTube channel. For the recording purposes, we have muted your microphone. But if you have any questions during the talk, please feel free to use the chat function to type up the questions so that we can raise them during the Q&A session. We hope that you subscribe to the YouTube channel and check out our past webinars if you have not done that yet. We also have an exciting program ahead of us as well, and the next seminar will be on April 13th with Dr. Asmeret Borhe at 10 a.m. Eastern Time on soil biogeochemistry. Emory Climate Talks started podcast series as well, and I hope you have already listened to one of our recent episodes. For example, with our speaker today, Dr. Talea Mayo. 3 Emory students, Gabriela Rucker, Eden Jonas, and Gina Kim, spoke with Dr. Mayo, and this episode was produced by an Emory alumna, Lauren Ballotin. We will post the information of our newsletter, YouTube channel, and the podcast in the chat shortly. Also today, I am so excited to be having this webinar with Professor Talea Mayo, who is an assistant professor in the Department of Mathematics at Emory University. I feel like I have been asking her to give a talk for so long, and I am so very delighted that this is actually happening. Professor Mayo was telling me that she is invited everywhere, and this is one of potentially 10 or so talks that she's doing this semester. So she's extremely busy, and I'm so happy that she made the time for us to come and share her research. Professor Mayo has a Bachelor of Science in Mathematics with the with the highest honors from Grambling State University in Louisiana. And she earned her Master of Science degree and PhD in computational and applied mathematics at the University of Texas at Austin. She had a very competitive NSF graduate research fellowship over there. So if you are a graduate student and are interested, you might want to talk to her. She did a postdoc in the civil and environmental engineering at Princeton University. And she was an assistant professor in the Department of Civil, Environmental and Construction Engineering, at the University of Central Florida in Orlando, Florida, before she moved to Emory last year. She is a computational mathematician, as her degrees tell you, and she is an expert in the development and application of numerical hydrodynamic models for coastal hazards. She will be telling us, I think, all about hurricane storm surge modeling that you wanted to know about, as well as the climate change impact on coastal flood risk and data assimilation methods that she uses in her research. I heard that she is now working on coastal erosion as well, so we might get to hear that as well. She is already so well accomplished and has so many awards, even though she is an assistant professor. She was awarded the Early Career Research Fellowship by the National Academies of Sciences Gulf Research Program, and she also received the Early Career Faculty Innovator Award by the National Center for Atmospheric Research. She is a fierce advocate of accessible, inclusive science and education of all people, and I cannot be more excited that she came to tell us about her work. She has been coming to so many of the climate talks as an audience to support this work. So thank you so much, Talea, and it is so great to have you as a speaker today, and the floor is all yours.
Great, thanks, Eri. When you say everything like that, it sounds so impressive, but I'm just a normal person and would love to chat with anyone who has questions kind of about this career. Always happy to kind of discuss that. So what I wanted to do today is actually, I am just going to focus on climate change impacts to hurricane storm surge risk. So I actually took out kind of the parts of some of the other work I've done, but if you have special interest in data assimilation or coastal erosion, definitely send me an email and I'd be happy to figure out a way to chat with you further about that. So now you're seeing slides, right? Okay, great. Right, so I am an assistant professor in the Department of Mathematics here at Emory. I just moved to Emory last summer, and one of the reasons I was so excited to come here was because of all of kind of the interdisciplinary work that's being done around sustainability and climate change, and Emory was definitely a really great motivator for wanting to be here. So I'm excited and so happy that we could work out a time for me to discuss kind of my work as it relates to climate change as part of this series. So I'll give you a brief introduction about hurricane storm surges and then say a little bit about how we model them numerically. And then I'll discuss kind of two projects that I've worked on. So both two different approaches, but both assessing kind of what is the impact of climate change on storm surge going to be. So coastal regions are the intersection of the complex physical processes in the built environment. So it's especially interesting for like civil engineering applications because you have the built environment, but then you also have natural processes that impact this area. And so this is a photo that I took in Hawaii, which is like the perfect illustration of what a nice coastline is, where you have all of the infrastructure and then you also have nature on the land and ocean all interacting. The coastal counties are home to more than 40% of the US population, and this population is expected to increase by more than 50% by 2060. So lots of people live in the coast, it's densely populated, and this is just increasing. Unfortunately, coastal regions are also at an increasing risk of natural hazards. And so as Ari mentioned, the two that I've focused the most on through my work are floods, and particularly hurricane storm surge flooding, and then also coastal erosion. So this photo is from Hurricane Ike. We took it right after Hurricane Ike, which struck the Gulf Coast in 2008. So it impacted Galveston Bay, which is right outside the Houston metropolitan area. And so we went on vacation there maybe like 6 months after it hit landfall. And this is one of the photos from there. So you can see this is one of the homes that was on the coastline that did not survive the storm surge from that storm. So what is storm surge? Storm surge is the abnormal rise of water generated by a storm. So if you're living on the coast or developing infrastructure along the coast, then you need to, at minimum, kind of prepare for the mean sea level and then also the normal high tides that occur every day. But storm surges are these extreme events that go above and beyond the predicted astronomical tide. So you might predict kind of the normal high tide, and then you have the storm surge, which is above that. And so then the total level of flooding you would expect from an event would be the high tide plus the surge, which we'll refer to as storm surge. So a lot of times those two terms are used interchangeably, even though a surge that occurs at low tide is obviously less impactful than one that occurs at high tide. But timing of storm surges can have a big impact on inundation. So when you're thinking about storm surges, just kind of physically, what is it? I think a good way to think about it is you have your bottom stress or your friction that's holding everything in place. And then you have a surface wind that comes from your storm that's basically fighting against that bottom stress. And so these are kind of the two dominant forces that cause coastal inundation. And so a lot of my earlier work was really trying to understand how to represent and predict or estimate what are the bottom stress parameters, because they are very important to storm surge modeling. And then also how do you represent kind of the wind field parameters, since that's the other major factor. So those are the two I've looked at the most. But significantly, storm surge poses the greatest threat to life and property from hurricanes, particularly in the US. And so Hurricane Katrina, for example, caused maximum storm surges of almost 28 feet in the Gulf Coast. And that's the storm that really got me interested in hurricanes and hurricane storm surges. So these days, as a storm is approaching landfall, the National Hurricane Center will actually issue its own hurricane storm surge advisory. So not just what are we expecting in terms of the storm, but what are we expecting in terms of the resulting storm surge, since that's the part that coastal residents really tend to suffer from. And so this is an advisory that was released during Hurricane Eta last year. So this is on Twitter, but it reflects kind of what's in the advisories on the National Hurricane Center website. And so they'll say kind of explicitly what's the risk of storm surge that coastal residents can expect. So here are a couple of photos from kind of historical storm surge events. So this one is from Hurricane Katrina, which flooded 80% of New Orleans. And again, that's the storm that really got me into this area. Here's another image from Hurricane Sandy, which struck the Northeast coast in 2012. And then this is an image more recently from Hurricane Harvey, which impacted, again, the Houston metropolitan area. And that occurred in 2017. And so kind of, I'll come back to this point, but what's interesting about all of these events is that storm surge was kind of the catalyst, but the devastation was caused by a lot of other factors. So for Hurricane Katrina, for example, the devastation was largely due to the failure of the civil infrastructure or the failure of the levee system. For Hurricane Sandy, a lot of the problem was the dense population that was in the region where the storm occurred. And for Hurricane Harvey, it was the combination of storm surge, but also inland flooding or freshwater flooding, which comes from rainfall. So that storm had kind of an unusual meteorological property in that it stalled over the Houston area. And so the tremendous amount of rain is what caused a lot of the flooding that happened. So storm surge actually like impeded the ability of that freshwater flooding to drain. And that's what really caused the devastation there. So we can model hurricane storm surges by what are known as the shallow water equations. And so the shallow water equations are a set of partial differential equations that describe H, the total height of a water column. So the height of the water from the bathymetry or the bottom surface of the ocean up to the surface. So if we know H, then we know how high is the water relative to this bottom. And then we can also solve for U and V, or these depth averaged velocities, or you could think of it as currents. And so these equations are coupled, and so we need numerical models to actually solve these. So they're too complex to be solved by hand, but we have these sophisticated models that do a pretty good job of kind of estimating them, solving them numerically. I guess I should mention why are they called shallow water equations? So the main assumption in shallow water equations is that you have these large horizontal length scales relative to the vertical. And so that allows you to simplify Navier-Stokes, which describe fluid flow. And so that's an assumption that's appropriate for coastal regions. So you can think of like the length of a beach is much longer compared to the depth. And that's why these equations are good for approximating the hydrodynamics in this area. So the two models that I use the most, the first is called ADCIRC, or the Advanced Circulation Model. This is kind of it has a really nice user community. So if you go to like adcirc.org, then you can download test cases, you can get the information to access this code. And then there's a nice like listserv where if you have questions about running the model, you can email in, and just the simplest questions like I'm trying to install it and I can't, to more complex, why am I getting the results? It's a really nice community. And there's also a users group. So we have meetings every year where students and faculty and non-academics can come together and discuss kind of their work on the problem, and also get trained in using the model. So this model, it discretizes the shallow water equations using what's called the continuous Galerkin finite element methods in space, and then centered finite differences in time. So different numerical methods to approximate the shallow water equations I showed on the previous slide. And so kind of the main advantage of the fact that it uses continuous Galerkin finite elements is that you don't need what's called structured meshes, or in other words, you can have kind of variable size in the mesh or numerical grid that you're solving over. So what you're looking at in this this figure, for example, this is the US coastline. So here's like Massachusetts, here's New Jersey, here's the Carolinas, here's Florida, and the Gulf of Mexico. And so these dark lines are showing these triangles, and at each vertex of the triangle, then we're computing H, and then the depth average velocities, the U and the V, described by the shallow water equation. So everywhere we have the vertex of a triangle, then we can estimate, for example, what's the storm surge at that point if we run the model. And so we're able to get more resolution toward the coastline than away from it because of the numerical method that we're using. So you can get kind of more resolution and more detailed modeling in the areas that you probably care more about, which is near the coastline. But this method kind of comes with a large computational expense. So one of the other models that I've used a lot is the sea, lake, and overland surges from hurricanes model, or what's called SLOSH. And so this model, it's significantly faster because it uses a simpler numerical method to solve the PDEs. The meshes are structured, so you don't, in theory, get the same like increased resolution near the coast, but we do get away with having more resolution near the coast by using polar coordinates. So you have, if you think about just a circle, having a smaller radius near the middle of the circle than the outer edges, then you have more resolution or more detail at the center of the circle. So like here, this is like a piece of a circle, so you'll have more grid points over here than you will away from the coastline. So SLOSH is the official storm surge model from the National Hurricane Center. And again, kind of it was developed to be simple, to take in simple meteorological input that National Hurricane Center was producing in real time, and then can kind of quickly simulate what's the storm surge that would be expected from a particular storm. So it runs quickly, and it also simplifies shallow water equations. So these models and others are used to forecast storm surges during hurricanes and guide emergency management and response. So here's a screenshot from the CIRA website, which uses AdCirc to predict what are the expected storm surges during a landfalling hurricane. And so this figure I actually accessed after the fact, so it's showing you kind of the maximum storm surges based on what we know actually happened. But if a storm were approaching land, then it would be based on the storm forecast. So it would continue to update as the storm approached land, and you could get some estimate of what the storm surge might be. And again, I mentioned earlier, the graphics and products that the National Hurricane Center produces too. And so those do something similar using the SLOSH model. So as a hurricane's approaching landfall, then we might know that this is kind of the level of storm surge that we expect. But then and you can use that to guide emergency management and response. So community stakeholders might use that to determine whether they should issue an evacuation or not. And coastal residents could try to understand, what level of risk they should be preparing for. But the question is, kind of outside of the emergency management scenario, how do we regularly prepare for extreme events that seem to be occurring more and more often? Okay, and so for that, we want to do kind of this storm surge risk analysis. So this is it's a matter of coastal resilience, right? So you don't want to just be prepared as a storm is coming. You want to board up your house and, evacuate or make these decisions to keep yourself safe. You also want to kind of longer term have coastal resilience. So maybe your house is elevated already so that, you're just in the long run better prepared for storm surge. And so measures you might take or a community might take are natural measures, nature-based features, structural features, and then non-structural features. So what this means is stakeholders might implement or try to preserve natural features such as like wetlands or things that just naturally kind of buttress hurricane storm surges. We can also work to implement or integrate nature-based features into the coastal communities to reduce the risk of storm surge. So an example of that might be building sand dunes, which we know will reduce some of the surge that might come. Structural measures would be things like levees or flood walls, right? So if you know the risk is high in a particular area, then maybe you take on the project of building a levee system. And then non-structural measures are things like policy implementation. So trying to do things that aren't just building, but that reduce risk maybe by relocating coastal communities. But if we're going to have true coastal resilience, then you need long-term planning and risk assessment. So all of these, knowing the best idea of what to do requires having some understanding of what the risk is long-term. And so for that, we do what's called risk analysis or risk assessment. And so here, this first part of the work, I'll talk about kind of probabilistic risk assessment. So when we're talking about risk, we're really concerned with the high impact, low probability events. So if we're looking at kind of a distribution of surge, so here are events and then the level of storm surge that each event caused. So this is saying like 800 events of the whole sample might produce between 0 and 0.2 or whatever this is meters of storm surge. We're not actually interested in what occurs the most often. We're interested in what has the most impact. So we're interested in this tail of the distribution, the high impact, so low frequency events. And so we can model these extremes using extreme value analysis. And so in my work, we've used the generalized Pareto distribution. So there are other distribution models where you can use to fit these type of extremes where you don't necessarily have a lot of data. And so what this distribution does is you set some threshold U, so you'll say, what are we considering extreme? And in this example, it's 2 meters and higher. And then we're trying to fit everything that's beyond there. So first we'll compute kind of what's the probability that we're in this region at all. So you might take the total number of events out here as compared to the entire number of events total. And then you'll fit this GPD model. And so you'll do that using these scale and shape parameters, but basically you're trying to fit this very limited data. And once you have the parameters that fit the data, then you can use them to compute what's called the return curve. So if I can, yeah, so if you look at this equation in the bottom, it has the same parameters that come from the generalized Pareto distribution, but now it's computing this H, and if I plot H against this return period, then I get what's called a return curve. So the way to read the return curve, it's basically giving you a measure of probability that a return level is exceeded. And so structural engineers use this a lot. So you've probably heard or may have heard of the 100-year flood. And so if I'm looking at this sample return curve, the 100-year flood is something like 3.5 meters. And so what that means is that in a given year, there's a 1 out of 100 chance of exceedance of 3.5 meters. And so the important thing is that it's probability each year. If I think about the 500-year flood, then it's 1 out of 500 chance of exceedance each year. So you could certainly have a 500-year flood occur 2 years in a row or 10 years in a row. It's just the odds are small. Okay, so the terminology is a little misleading. And so I wrote an article for the notices in the bulletin of the AMS in 2019, kind of just describing this idea of the 100-year surge and what does it mean to be called that. Okay, but once you have this return curve, the point is it tells you a lot about the risk. So if I have to build something that can withstand the 100-year flood level, then I understand that it needs to be able to withstand 3.5 meters of surge. So again, the return curve is coming from the model of these low frequency and high impact events. And so for a given location, it's low frequency. So presumably you don't have sufficient data. So if I want to know what's my risk in New Orleans, then probably there haven't been this large sample of storms to determine this curve by. And even if you are in some place or you expand your definition of local so that you do have enough measurements of storm surges, it's not really useful or reliable for understanding your risk under the threats of climate change. So you may be able to understand kind of what's your current risk or your past risk, but that doesn't necessarily tell you what you need to know about your future risk, which is what we're really trying to prepare for when we think about coastal resilience. So for that, like our approach to that is to generate the data ourselves using numerical modeling. So the synthetic hurricanes can be generated by meteorologists, and so that's what we use. So they're developing for a given location 2,000 to 3,000 synthetic storms. We kind of select the ones that come close enough to where we're interested in computing risk, and then make sure that they're strong enough that they're likely to produce surge in this tail end of the distribution. And then we can also use the same methodology to generate synthetic hurricanes that are representative of different climate scenarios. So for this work, for present day climate, then we're generating the synthetic storms using what's called the NCEP-NCARB analysis, or basically present day climate data is being used to produce the synthetic storms. And then we can also use global climate models that implement various emission scenarios. So for this work, I'll show RCP 8.5, or kind of what was expected or considered to be the worst case scenario using global climate models, and then use that data to generate the synthetic storm. So in the end, you have kind of this suite of storms, 2,000 to 3,000 storms, they're representative of either present day or end of century climate conditions, because that's the data that you're giving it. And this isn't the work I do. So I work with other atmospheric scientists who use kind of their models and climate data to produce these. But then what I can do is push these through my storm surge model. So use my storm surge model with these storms and produce them. What are the corresponding storm surges for each of these 2,000 to 3,000 storms? And so I get the distribution like this, and I can fit it and understand kind of what's my risk for a given location. Additionally, when we think about climate change impacts, we also think about sea level rise. So not only are the storms themselves changing, but we understand that locally sea level rises are increasing or decreasing depending where you are. And so mathematically, you can estimate kind of this distribution of sea level rise. I mean, you could just add on what's the mean value, but we have kind of more information than that. And so you can convolve the two distributions to get an understanding of what's the expected flood levels. And so we get this distribution from other sea level rise experts, and specifically Robert Kopp at Rutgers. So once we have all of this information, then we can assess kind of what's going on at different locations. The location that I'll show you is Jamaica Bay, New York, which is an area on the bottom of Long Island. So here's the New York area, this is Long Island, and then here's Jamaica Bay right at the bottom here. And then we also did this same experiment for 3 other sites, so Narragansett Bay, Rhode Island, Atlantic City, New Jersey, and Norfolk, Virginia. And so these locations were chosen, they were given to me in collaboration with landscape architects because they were susceptible to inundation, so they were at physical risk of storm surge, but also socioeconomically vulnerable. So really in need of this kind of information so they can do better planning. So for Jamaica Bay, New York, when we computed the return curve using this methodology, then we found for present day climate conditions, the 100-year flood was 3.3 meters. And so if we convolve that distribution with the sea level rise data, then we get this green curve for the mid 21st century. And so what you see here is that what was the 100-year flood becomes the 57-year flood when we account for sea level rise. And so basically, this level is kind of 2 times as likely in a given year to occur. Similarly, if we use sea level rise data from the end of the century, then we see the 100-year flood become the 29-year flood, or something like 4 times as likely to occur by the end of the century. But this only is accounting for present day storms and then kind of later or mid to late century sea level rises. And so what we know is that the storms are also changing. So it's not just that the sea level is going to rise. A problem is also that the storms themselves are changing. So they're becoming more intense. The frequency of occurrence is changing. Most models agree they're becoming more intense. So we want to know, how does that impact risk as well? And so we can assess this by using climate model data. And so if I look at kind of the present day risk, then I get this dashed curve. And so it's slightly different than what I got using the observed data, but it has the same behavior. And so I can then integrate the storm climatology for the middle of the century along with the sea level rise for the middle of the century. And so what I'm seeing is that what was the 100-year surge is moving even further. So it becomes the 34-year surge. So what this is saying is that if I just account for sea level rise, what was the 100-year flood becomes the 57-year flood, or it's almost 2 times as likely in a given year to occur. But if I also consider that hurricanes are changing in intensity and frequency, then I see that become even more probable, so almost 3 times as likely in a given year. I can also do the same thing to observe risk at the end of the century. And so I see that once I account for changing storm climatology, what was the 100-year surge becomes the 6-year surge, so much more likely to occur each year. And so if we're planning long-term for a coastal community, then if I want like a structure that's going to be around for 100 years or mid-century, then I really need to be using one of these dash curves to build for that. So we did similar work for the other 3 sites, so Jamaica Bay plus the other 3, and then this is more or less showing you how the risk is increasing over time for various flood levels. So the 100-year flood is in this second row, and so you're seeing kind of what's the present day risk, what is it by kind of the middle of the century and these 2, and then end of century, and then we did it for this entire region. Working with GIS modelers and landscape architects. And so if you go to this website, the landscape architects have kind of presented different resilience measures. So kind of like layered approaches to kind of doing something about this that might be useful for stakeholders. The work is also described in this book by Nordenson et al. And that came out in 2018. So that describes kind of more comprehensively the whole project and not just the modeling, but the application of the modeling. And then we'll have a paper coming out this year that just describes the numerical aspects of it. So probabilistic modeling, like I just showed you, depends on these synthetic storms, which are generated from a statistical model. but the computational costs can be prohibitive, right? So I have to be able to simulate these thousands of synthetic storms. And so for that reason, we use the slosh model, which is faster. Similar studies have used kind of coarser ad-circ meshes, but the idea is kind of you have to sacrifice some of the detail that you have in your numerical grid so that you can do so many simulations. So another approach to understanding changing storm surge risk is to assess it deterministically. And so that's what I've done in this kind of second part of the work. So we had a paper that came out late last year, and I'll reference it at the end, but basically this is the approach we took. So we looked at hurricanes and then we looked at them again under climate change conditions and just compared the two simulations. And so this allowed us to kind of get away with much more detailed modeling. So the WRF model is an atmospheric model. It's three-dimensional, it's convection permitting, it's a regional climate model. It has really high resolution in both the horizontal and vertical directions. So these are things that the atmospheric scientists like. It's a good model for regional climate modeling. And so what we did was we used this model to assess kind of what do storms that have already occurred. So between 2000 to 2013, could we re-simulate them imposing a climate change signal? So the end of century climate change signal on the boundaries. So it would affect things like sea level, pressure, geopotential height, air temperature, and other things that actually affect the development of the hurricanes. And so then we modeled the surge from both. So we modeled the hurricanes as they occurred and then how they would have occurred had this climate change signal been implemented. And so then because we just kind of have two storms to compare, the present day storm and the future storm, then we can use the ad-circ model and we can use a really detailed mesh. And so that's what we did. The mesh we used is called HSOFS. And so what's special about this mesh is it has 1.8 million vertices, which for you means that's the number of places where I'm computing storm surges, right? So I have so much detail along the coastline where normally I couldn't have that much detail. But it's also interesting because it has overland grid resolution. So I'm not able to just model what's going on in the coast. I actually can use this model to see what's happening overland. And so the resolution, it's not amazing, but it's pretty good for this size of a mesh. So here's one of the scenarios that we ran. So Hurricane Ike, as it actually happened or under present day climate conditions. And then we modeled it again under end of century climate conditions. And so if we just kind of look at what's happening over land, this is the Houston area, Galveston Bay is down here, and then this is the Gulf of Mexico. So just kind of qualitatively, you can see that there's significantly more red or higher storm surges for the end of century simulations. And then quantitatively, then we see the inundation volume increase. So the volume of water that actually ever goes on land increases from 23 cubic kilometers to 30 cubic kilometers. And then same with the inundation extent. So not just how much water, but like how far does it go? And so that also increases from 16,000 square kilometers to 17,000. So we did this for kind of all of the storms that we were simulating, which I'll show in the next slide, and then computed the differences. So red value basically means that we saw more storm surge at the end of the century simulation versus the present day simulation, or things are getting worse. And so you can see there's a few places where you have blue, so you have like less storm surge at the end of the century for the present day, but overwhelmingly things are red. And then that's kind of quantified in this table. So here are all the storms we ran. They're listed in order of the initial control volume. So how much inundation was there in the present day scenario? And then when we model with this climate change signal, what's the new inundation? And so here, for example, you can see a few places where the total inundation does decrease. And so that just has to do with the variability of how the storms change and then also how the tracks change. But on average, things increase. So we expect by the end of century, we're going to see something like 36% more inundation for the same storms if they were to occur. And so another interesting thing is that the volume changes are not directly related to kind of the changes that we see in the hurricanes. So for example, if I think I highlighted, yeah. So if we're looking at, for example, Isabel, red basically means the intensity increase. So the wind speeds increase, the radius increase, or the size of the storm increased, translation speed decreased, which means it slowed down, which generally would cause more surge, pressure decreased, so it intensified, but it doesn't necessarily mean that the inundation volume increased. And similarly, like for Dennis, we see everything kind of decrease or de-intensify, but the actual inundation intensified. And so this was interesting to us because it basically just shows that you can't really predict what the changes are going to be without the explicit modeling. Similarly, if we kind of look at the data from present day and end of century data, so this blue section is wind speed. So you might think of that as like category 1 storm, category 2, and the darker color is going to represent a stronger storm. And it's not always the stronger storms that produce the most inundation. And that pattern or lack of pattern is also observed for the end of century data. So the point is kind of that storm surge risk is not directly related to storm intensity. And so when we think about the future, it's something that we need to explicitly model. We can't try to make assumptions based on what's known in the meteorology. So just some concluding thoughts, and then I'll take any questions you have. Surge is a low probability but high impact hazard. So it doesn't happen often, and especially the high impact events don't happen often, but when they do happen, they have the potential for great devastation. So how low probability is greatly impacted by, for example, what's the changes in tropical cyclone frequency. So how often are storms occurring in the first place? And this is something that's uncertain, especially understanding what's going to happen at the end of the century. High impact, how high of an impact is greatly impacted by a lot of things. So this includes tropical cyclone characteristics, so intensity, size, translation speed, and the uncertainties of all of these. And then also other things that intersect or interact with the physical hazard. So again, for Katrina, the impact was greatly affected by the levee failure. For Sandy, it was affected by population density. For Harvey, it was affected by other meteorology, so the compound flood event, and also the infrastructure. So the level of building that had been done in the Houston metropolitan area contributed to kind of lower frictions, which facilitates more surge. So numerical storm surge modeling is an essential tool for risk assessment, and especially as we think about the impacts of climate change. But I think more and more we're seeing kind of how critical multidisciplinary research is to truly addressing coastal resilience. Okay, and so let me just point you to this paper is the one that we put out that discussed kind of the deterministic comparisons of risk and how it was increasing. And then with that, I'll take any questions you have.
Well, thank you so much, Talea. That was so great. And I'm actually already seeing one question pop up. But if you have any questions, please feel free to put that in the chat and we will go over that. So the first question is from Klaus. He asks, how many cores did you use and how long was the computation time?
Yeah, so for the answer, so the slosh modeling where we did the probabilistic models and we had like 2,000 simulations per scenario, we actually did that using like a desktop basically. And so we at some point kind of put it on a cluster, but those are simulations that can be run locally. So you don't need to do any cores, and that's why we use that model for the project. For AdCirc, the simulations I showed that use like the 1.8 million mesh. So it kind of it depends a little bit about the length of the storm we're simulating. There's some variability, but I'm pretty sure we use something in the like the order of like 200 cores, and it'll take maybe 2 hours to simulate one storm. So again, that's why we're using AdCirc for the deterministic modeling and then Slosh for the other.
Okay, there's a lot of questions coming up. So Devjani asks, do you consider if or how riparian buffers or coastal vegetation like mangroves influence the inundation from storm surges?
Yeah, so that is it. It's not my specific area. It's kind of built into the meshes that we use. So the numerical meshes that we use will just, especially the one that I showed, so HSOFS, already has a mesh developed where they've already input kind of parameters that describe bottom friction. Bottom friction is what we usually use to kind of coarsely explain coastal vegetation. So yes, but it's kind of built in and it's not something like I actively study. I had an undergraduate research student a few years ago looking at that. So he was just kind of changing the bottom friction to represent different things. And also my PhD thesis was more or less how does bottom friction affect the hydrodynamics, but it's not like an active area that I study. Like if we put this in, what does it do? This is kind of like multidisciplinary role for somebody that I would work with.
Great. So David asks, I know you did not talk about erosion, but the barrier islands seem fragile to surge. Can that be modeled?
Yes. So yeah, I would say that the model we use for erosion is X Beach. They are very fragile to surge. So the simulations like we've most recently done were Hurricane Katrina and Ivan. And so I think it's Katrina, maybe I'm remembering it wrong, but one of those caused actually a breach for an island in off of Alabama. So it is something that we model. The model that we use is called X Beach. And the paper that we have coming out about that, it's more about wave energy conversion and trying to use wave energy conversion to actually prevent some of that and some of the breaches, but it kind of includes those details. And I can, of course, provide like more references about the modeling that's done for that. So what we usually do is couple kind of the AdCirc simulations or the storm surge simulation and use that as a boundary condition on the erosion model. And then we're able to kind of assess what's the resulting erosion.
The next question is from Kip. And the question is, are your results used and broadcasted by the National Weather Service?
Yeah, thank goodness. No, because that'd be too much pressure. But yeah, so I don't really focus on real-time forecasting. I focus on model development. So kind of my goal is to have like longer term information. I think one, I'm very uncomfortable and it's way too much pressure to try to predict in real time. But also, as I was saying, like for coastal resilience, you really wanting to understand long-term risk. So no, it's not, but it's not the application that I work on.
So Christian asks, are you able to consider more GCMs as opposed to just GFDL one? Did you only use one because of computational time?
Yeah, so what I presented was GFDL, but in that actual study, we used 4 of the 19 models that were from the IPCC report. So yeah, you could use as many models as you had. It's just we used the 4 that we used because we felt that they spanned the range of kind of possibilities of what the models show. But you can definitely do that. And then again, to just kind of emphasize, I use the hurricane data as an input. So it's not actually my work where we're developing the hurricanes, which are coming from the GCMs, we're collaborating with someone who's done that. But yeah, you can use more.
Kina asks, she says, fantastic presentation. She goes on to say, I have heard that the Army Corps of Engineers prioritizes its coastal restoration and resilience efforts based upon a cost-benefit calculation related to the market value of developed property. If true, is it harder to get priority to undeveloped wetlands and other natural areas? Also, it seems such valuation would prioritize wealthier communities with higher market values.
Yeah, so I don't know explicitly what Army Corps is doing as far as resilience efforts, because things kind of like shift around and depend on what community you're looking at. But I am familiar with this idea of people translating risk into estimates like or monetary estimates based on property values. And that's the exact kind of criticism that I've heard about doing that, is that, you know, it inherently just makes the wealthier communities high priority. So I don't know, but I have also heard that. And so I don't know about priorities as far as like Army Corps. I do know that, I mean, I would say kind of resilience falls on a lot of different stakeholders. So not just Army Corps, but like, for example, the project Structures of Coastal Resilience was funded by Rockefeller Foundation. So it's kind of like for every community, you kind of have to piece together the resources you have or the stakeholders who are interested to assist in improving resilience. And I don't think there was like a really good kind of homogenous effort. But yeah, I don't really disagree with anything. I don't really know what's being done. And I think it's hard to say kind of on a national level what's being done. It seems like a very local issue. So, you know, a problem of like mayors even, where it can completely vary from community to community.
And it seems like it must be very difficult to actually get all stakeholders that need to be involved, especially from the minority population or the people that are really impacted, to really come and raise the voice. So that's also
right. Yeah, and I think that's kind of a lot of what you've shown through the climate series, right? Is just how, you know, how important it is to have different voices, because obviously kind of what we're doing doesn't really work, but I don't have solutions, but hopefully things get better. I think the need is becoming more and more apparent.
Right. And I think what you're showing is so important, because you can really tell which part of the areas can be really impacted, right? So that's great. Kip says, sounds like this work is ripe for Bayesian modeling, continually updating based on accumulating data.
Yeah, and I mean, I've done a lot of, I mean, I guess there's different ways you can implement this. Right, so I've done kind of data assimilation, which comes from the same kind of theoretical framework to update parameters that are just on the model. I think for kind of long-term risk assessment, again, it's difficult because you actually don't have that much data over time, right? Like you don't have that many storm surges that impacts a particular area, but certainly with just within the modeling, this is an approach that's being used more and more. So like at minimum, can we make the models better, or can we get the real-time forecasts to be better? And if you look at like some of the earlier papers I've done, that's kind of the goal, more towards that. So I guess I need to put more thought into like how it can be applied to long-term risk analysis, because again, your data is pretty limited.
Michael says, how do you validate the models that are generated?
Yeah, so there's so many levels of modeling in this work, right? So we're going from climate model down to like regional atmospheric models, down to the storm surge model. So there's definitely a lot of uncertainty at a lot of places. So I'm just going to talk about this storm surge validation, because that's the part, you know, that I do. And so for AdCirc, there's basically a lot of papers that validate against different storms. The particular mesh that I showed, there's a number of different validation methods that they used, but basically they validated this one mesh for a number of storms. And so they use kind of a combination of data like high water marks. So the data is hard to get, even like the non-modeled data is hard to get too, but it's generally validated against that type of stuff. So elevation data, how you can get it, either what is recorded at a particular gauge, which is just one place in time, but then also kind of like less sophisticated things like high water marks. Did you accurately produce the highest level of water for a given storm? And then another complexity that comes in is like, how do you represent the hurricane? Because so if your model doesn't exactly match, it can be because you didn't represent the wind field correctly. But I think that's kind of the not so short answer. So against tidal data, gauge data, USGS data, and then the models, like when we say models, can vary based on which mesh you're using. So the mesh that I showed, that's kind of from there. For slosh, I actually wrote a paper where we were trying to validate against just tide gauge data. So again, you're kind of limited in space because you just don't have the amount of data that you really need to fully validate or verify. I hope that answers the question.
Yeah, that's great. I remembered listening to your talk about what you said at the Amplifier podcast episode, that there's so much machine learning going on, but that's really not enough, because what machine learning can do is to look at the past and cannot look at the future, because we need to understand the processes. And I think that's so important. And, you know, we cannot just rely on the past to really understand what's going to happen in the future. And I wonder, right now, there's so much warming in the Arctic, and a lot of scientists are finding the Arctic Ocean circulation changing, etc. That's going to also impact the storm surge as well, potentially, and then the sea level rise. And I have no idea how much is actually considered in the climate model yet. But what is your the next model development that you're looking at?
I guess what we're looking at right now is a lot to do with kind of what it's difficult to predict like without explicit modeling. So we're trying to see what we can learn about uncertainties within the storm itself. So that's the thing we're looking at now. So basically, how much is the uncertainty in our wind going to impact, uncertainty in our storm surges? And then can we quantify that? So just kind of mathematically, you would call that like uncertainty propagation. And so I guess kind of related to the last question that someone asked is, well, you can't really get rid of the uncertainty, but can we at least see how it's going to impact our results? And then we know, like, even if we don't know how exactly the melting of the Arctic would affect sea level rise, would affect this, can we quantify like the range of possibilities based on what it might do?
Yeah, I totally love that. I feel we don't do enough of that. Like, I work on emissions and we have so much uncertainty, but then usually we put in just one set of emissions in the model. So I think we need to do much more of that. So Debjani had a comment: changes in coastal geomorphology and sediment transport with storm surges and hurricanes are tracking attractions to build carbon cycle processes in the Department of Energy ESM. I guess energy exascale Earth system model. Maybe food for thought to expand your hydrodynamic modeling in the future. So many opportunities.
Yeah, thank you.
So it is 5 o'clock. So if there's no more questions, I think we had such great conversation and such great presentation. There's so much to think about. And I think this gave us a lot of thinking for our potential collaboration. So thank you so much, Talea.
Thank you.
And thank you everybody for joining. Stay safe and healthy.